Section 6.1, Composite Functions. So back in, I believe it was section 3.1, we learned how to combine two functions f and g by adding them, subtracting them, multiplying them, and dividing them to get a brand new function. There is another way you can combine two functions to produce a new function. We didn't talk about it back then, but we will now, and that is through composing the functions. Okay, so in this section, we are going to concentrate on the composition of functions. It is a way of taking two functions and putting them together to make a brand new function. So we're going to start with the definition of a composite function. It says given two functions f and g, the composite function f, and then you see a little circle in the middle, an open circle, g, okay, you read that as f composed with g, or you can also call it f of g. It is defined in the following way. Okay, so if you read in the box, it says that f of g is equal to f of g of x. Okay, so basically what you need to get from this, and we'll go into detail about what this means. First of all, you need to be able to recognize this going forward. Okay, so back in the day, if we saw f like fg just like this, okay, this is multiplication. Okay, if there's nothing in the middle of f and g, it's understood to be multiplication. Similarly, if you have just a dot like this is also multiplication. Okay, but now you've got this brand new symbol with this little open circle, and that is the symbol for composition. Okay, so make sure you understand the difference between composition and multiplication. Okay, so the little circle just indicates composition. Okay, you may not be given the circle. You may see it written this way, f of g of x. Okay, that's indicating composition as well. Okay, all right. Order matters with composition. Okay, if we think back to what we learned in 3.1, okay, when does order matter? And when does order not matter? So I'm just making a little list up here. Order does not matter. Okay, so what we learned in 3.1, okay, if you add two functions, the order does not matter. Okay, f plus g is the same thing as g plus f. Okay, but if you subtract two functions, f minus g is not necessarily the same as g minus f. So with subtraction, order matters. Okay, and then we talked about multiplication. Okay, if you think of two numbers, 4 times 5 is the same thing as 5 times 4. So with multiplication, order does not matter, even if you're multiplying functions. Okay, division, order matters. Okay, if I do 10 divided by 2, that's different than 2 divided by 10. Okay, same with functions. If you're taking two functions and dividing them, it depends, you know, it matters which function is in the numerator. Okay, so order matters with division. Okay, so now we're taking two functions and making a new one through composition. And what you need to know, even though we haven't composed anything yet, order is going to matter for composition. Okay, so it depends on whether you're doing f of g of x, or if you look in the box below it, you see g of f of x, which is, you know, this g of f of x. That's different. Okay, if you look at these guys, okay, so I'm going to put f of g of x here, okay, and then I'm going to look at g of f of x over here. Okay, they are different. Okay, basically what's going on with composition, if you look at both of these, there is an inside function and there is an outside function. So if I take a look at f of g of x, what you can see here is that on the inside here, we have g. Okay, so g of x is considered to be the inside function. Whoops. So g is the inside function. And then on the outside, you have f. Okay, so f is the outside function in this case. But then if you look at g of f of x, okay, in this situation, f is the inside function. And this time, g is on the outside. Okay, so that's kind of the hallmark of composition. You have an inside function and an outside function. It's going to matter which function is on the inside and which one's on the outside. So the order you do composition in is going to matter. Okay, sometimes f of g of x will be equal to g of f of x, but not always. You've got to go into it that order matters. You've got to pay attention to which function is on the inside and which one is on the outside. Okay, all right, so now we're going to talk about how you do composition, what it actually means. Okay, so let's go down here to this bullet point. It says, think of composition of functions in this way. Just as we substitute a number into a function, we may substitute a function into a function. Okay, this statement right here just summarized what composition is. Okay, and I'm going to kind of translate it. What we're doing with composition, okay, instead of plugging a number into a function, that's what we're used to doing. We're actually plugging a function into another function. Okay, so what composition is, in a nutshell, is we are plugging one function into another to get a new function. Okay. All right, and we're going to do plenty of examples so you can see how this works. Okay, but this is what you have to remember. Okay, we're plugging one function into another. Okay. All right. So in the second bullet point here, this is what I've already said. Okay, order is going to matter. F of g is not always equal to g of f. Okay, sometimes they are equal, but you can't bank on that happening. Okay, and then let's read this statement. This statement is going to talk about the domain of f of g. Okay, and of course of g of f as well. Okay, if you remember when we added functions earlier and we subtracted them and we multiplied them and we divided them to make a brand new function, the brand new function has the same properties of all functions. So you can talk about the domain of the new function. Okay, so similarly here, what's going to happen is we're going to form all these composite functions, and once we get our new function, we're going to have to state its domain. Okay, but I'm warning you here. The domain of composite functions is tricky. Okay, I'm going to read this statement and you're going to see how tricky it sounds. Okay, it says the domain of f of g is the set of all numbers x in the domain of g such that g of x is in the domain of f. In the same way, the domain of g of f is the set of all numbers x in the domain of f such that f of x is in the domain of g. Okay, as soon as you read those two sentences, you're like, what? Okay, so don't read too much into what that says right now, but just remember what I'm telling you as we go into the examples. Forming the domain of a composite function is tricky. Okay, but I'm going to walk you through how to do it. Okay. All right, before we get into examples of composition, okay, I want to show you a little illustration of what composition is. Okay, so this is a function machine. Okay, it's basically showing you the composition process. Okay, this particular illustration is for this direction. This is for f of g of x. Okay, so remember, any function that we have, we plug something in and we get something out. X is always our input. Okay, so we're starting with x in the very middle. Okay, we're taking our x and we're plugging it in. We follow the order of operations. Okay, so we're going to do what's in parentheses first. Okay, so the first thing that's going to happen is that x is going to be plugged into the inside function. Okay, so x is going to be sent to g. Okay, because it's the inside function in this situation. Okay, so g of x is going to be its own rule. Okay, so you're going to plug x into g, and that's going to spit out some output, which is g of x. Okay, so let me write this out. X is going to get plugged into g. Okay, that's going to give you some output g of x. Okay, and then whatever that number is, okay, so here's x, it goes into the machine, okay, it goes into g, okay, g is going to do something to that input and produce an output. The output is going to be g of x, okay, and then that output g of x is plugged into f, the outside function. Okay, so then in the little illustration here, you see g of x, okay, then g of x gets sent into the f function. F is its own rule. It's taking the input, g of x, and it's going to spit out a new output, okay? And then, so this g of x gets sent to f, okay? F is going to change it, okay? And it's going to spit out an output, which is going to be f of g of x, okay? So basically, that's what's going on here. You see the x, it's plugged into g, okay? That spits out the output g of x, and then that's plugged in as an input to f, and then that's going to spit out the output f of g of x, okay? So basically here, for f of g of x, you start with an input x, it's plugged into g, that spits out an output g of x, that becomes the input to the f function, okay? F is going to change that input into an output, and the resulting output is going to be f of g of x, okay? And a similar kind of thing happens if you're doing g of f of x, okay? It's just, you know, your outside and your inside functions change, okay? But going into the examples, we're about to start them, you need to remember a couple of important things, okay? Composition of functions is basically a way of taking two functions and putting them together to make a new function, okay? There's going to be an inside function and there's going to be an outside function. We are basically plugging one function into another, okay? And you're going to see in a minute, we're always going to be plugging the inside function into the outside function, okay? Order matters. So if you're doing f of g, you're not necessarily going to get the same thing as if you do g of f. Okay, and then finally, with composition, we will be taking two functions and making a new one. So you are going to have to find the domain of your composite function, and that can be a bit tricky.